Now we're going to talk about the trip operon. Trip, as in tryptophan, which is an amino acid. So the trip operon is negative repressible. Negative meaning it has a repressor. Repressible meaning it's on, but you can turn it off. Okay? And this is going to depend on the levels of tryptophan in a cell. So the trip operon has the promoter and the operator. Then it has several genes, so trip E, D, C, B, and A. And somewhere upstream, it has trip R, which has regulatory function. Trip R makes the trip repressor. Okay. All of these enzymes help us to make tryptophan. So if tryptophan levels are low, this needs to come on so we can produce tryptophan because it's necessary in our cells. So that's going to be different than what we did with the lac operon. Okay. So if we have low levels of tryptophan, so we make our repressor, but our repressor can't bind to the operator, so we are transcribing this so that we can now produce more tryptophan in our cell. If we have high levels of tryptophan, that tryptophan serves as a co-repressor, so it binds to the repressor, changes its shape, allows it to bind to the operator. When this tryptophan binds to the repressor binds to the operator, we turn it off. But it's not that easy. So the same thing with lac operon, we have two levels of control. So one is the repressor, the other is this idea of attenuation. So attenuation means we start transcribing it and then we stop because we realize, oh, we don't need it after all. So we can still terminate it before the whole thing is made. And that's this idea of attenuation. So if tryptophan levels are high, then we can stop this. Okay? So for attenuation to occur, we have to have several sequences that are a part of this. So here we are where we're making our trip. It has this leader sequence here that codes for tryptophan. So think about that. If you have this leader sequence that codes for tryptophan, that means you're sensing the environment then trying to see if you have tryptophan A. Also remember that this is an RNA molecule. If RNA molecules combine to each other, they have to have regions of complementation. So here we have several regions that are complementary. So 2, so it's 1 in green here, 2 in yellow, 3 is this blue sequence, and then 4 is this reddish sequence here. So 2 and 1, 1 and 2 are complementary, 2 and 3 are complementary, and 3 and 4. Okay, so 1 and 2, 2 to 3, 3 to 4. Those are all complementary. You'll also notice here we have a U-rich attenuator. So remember that U-rich sequence was important. A hairpin sequence and a U-rich sequence were important in row-independent termination. So that comes into play here too. Now, we have started to transcribe, but here, for some reason, our translation is not coupled with our transcription. Okay, so when that occurs, 1 and 2 bind, 3 and 4 bind. By this binding happening, we have this row-independent termination. So we have this hairpin structure and this U-rich. So no transcription occurs. Okay, so in a condition that no translation occurs. In the condition that translation is not coupled with transcription, 1 binds to 2, 3 binds to 4. We have this U-rich region that causes row-independent termination and no translation. Then we can have low levels of tryptophan. Okay, so now transcription and translation are coupled. Our tryptophan levels are low. And because our tryptophan levels are low, we pause. So remember we have this leader sequence, and some of the first couple amino acids that we produce are tryptophan. Well, because we don't have a lot of tryptophan, we can't have it bound to our tRNA, we can't proceed. So our ribosome stops and waits. And as it stops and waits, it's going to allow, it covers, so think of this as like blocking some sequencing. And so it's blocking 1, so 1 can't bind to 2. This leaves 2 to bind to 3, and therefore 3 and 4 can't bind. Okay, so now our polymerase can go ahead and finish transcribing. And if it can transcribe it, we can translate it. Okay, so low levels of tryptophan, and because tryptophan is necessary in our leader sequence, it causes a pause. As our ribosome is pausing, it's going to dictate how these stem loops can form, and therefore by 2 and 3 binding allows transcription to continue, which is going to allow translation to continue. Now, another condition, we have transcription and translation. They are coupled again. Now we have high levels of tryptophan, so we don't need to pause, right? And so because we're not pausing, we're going to stop in an area that blocks 1 and 2 from binding together, and 2 and 3 binding. So this allows 3 and 4 to bind. If 3 and 4 binds, now we have a hairpin with that U-rich region, and we're going to terminate. Okay, so I know this is a little bit confusing, so let's back it up again. So with tryptophan is necessary to Operon is necessary to produce tryptophan. Okay, so the first idea is if we have low levels of tryptophan, we need to turn this on. We need to produce that molecule. Okay, so the first level is this repressor. If we have low levels, the tryptophan is not bound to the repressor is not bound to the operator, transcription can occur. If you have high levels, tryptophan binds to the repressor, changes it, lets it bind to the operator, we turn this off. We already have some tryptophan, we don't need to continue making it. But if we have high levels of tryptophan, we can have attenuation. So with attenuation, it matters on the sequence. Okay, so remember that 1 can bind to 2, 2 can bind to 3, 3 can bind to 4. If 3 binds to 4, then you have this U-rich sequence that causes termination. So if 3 binds to 4, we're terminating this. Okay. So when translation is not coupled with transcription, so we are trying to transcribe this, but we're not worried about translating it. So we're trying to transcribe it. Well, we transcribe it, and what happens is 1 binds to 2, 3 binds to 4, the U-rich region is there, it's terminated. 3 and 4 equals termination. Well, if we couple the 2 now, so now we are translating and transcribing at the same time. Our tryptophan levels are low. We need to make this molecule, right? So we start to translate it. We pause because we need to incorporate tryptophan. Well, because tryptophan levels are low, we can't incorporate it. So our ribosome is sitting here waiting to be able to use the tryptophan. As it's waiting, it's stopping 1 from binding to 2, allowing 2 to bind to 3. Because 2 binds to 3, 3 can't bind to 4. Therefore, we don't worry about this attenuator sequence. And so transcription can continue, and once this continues, translation will be able to continue. Then we have transcription and translation coupled again, but now we have a lot of tryptophan. So because we have a lot of tryptophan here, we're not going to stall in the same way we did before. Okay? So now we're going. So 1 doesn't bind to 2 and 2 doesn't bind to 3. That leaves 3 to bind to 4. Well, 3 binds to 4, attenuator sequence, this is going to stop. Right? So I want you to note here the difference between catabolism and anabolism. And this is something that you also should have learned in a previous class. So catabolism is the breakdown. So we are taking a large molecule, breaking it down into the smaller subunits or the monomers. These tend to be inducible processes. Okay, so the breakdown of large to small is off, but you can turn it on when necessary. Anabolism is when we're building up. So we're taking the small monomers, building a large polymer or molecule. These tend to be repressible, so we are doing them until we don't have to anymore, and then we turn them off. Okay. So any questions, comments, or concerns on TRIP?